Today we're going to start chapter 7 and our focus is going to be optimization. And so we're going to start off with solving problems really how you probably would have done in calculus, but then we'll move to some other techniques. Okay. So we have an oscillating current in an electric circuit is described by I equals 9 times e to the minus t times sine of 2 times pi times t, where t is in seconds. And the question is, when does the current reach its maximum? Okay, so why don't we first just get an idea of what this looks like, and then we can maybe work from there. Okay, so let's maybe start off with some t values. Okay, and since we have really no idea what this really looks like here yet, why don't we just say 0 to 10, okay, which is going to be plenty. Okay. And then we could say I equals, and why don't I actually just copy and paste this? Although there are a few notes I should probably make as we type it in. Okay. So MATLAB will create a vector here when it does e to the minus t. Okay. And is what that vector is really going to contain is e to all these different values here in a vector. Okay, and of course it'll multiply them by 9. It's just scalar multiplication. And similarly over here we'll wind up with a vector, and that vector will be sine of 2 pi times all those t values. Okay. Now we will end up with a vector times a vector, which means that the dimensions aren't going to be the right dimensions for matrix multiplication. Okay, so that's why we have this dot here, so that we'll multiply, the first entry of the first vector by the first entry of the second one, and so on. Okay, so that's all set up. Okay. And let's see, let's go ahead and plot t comma I. And if this doesn't look smooth, we can go in here and we can use more t values. Right? And so it's not looking super smooth, but you actually can see about where that maximum is occurring. Let's smooth it out a little bit though. There we go, that looks a little better. Yeah, you can see that maximum up here. That looks like it's telling us it's about 0.24. Okay, but let's zero in on this a little bit because it's just approximate here. Okay, let's maybe use our bisect function. Okay, and so I'm going to actually maybe for now just comment out these plots because we're not going to need them. But I'm going to want to be using I as an inline function here, so I'm going to write at t. And then let's go ahead and use our bisect function, so bisect. Okay. And we want our function. Okay. And then we'd like to kind of surround that root. And we saw it was, I shouldn't call it a root yet. I was about to say we'll do bisect I, and we'd put maybe 0.1 to say 0.4. We think it's in between there. Okay. Or actually, let me go a little bit bigger, 0.6. Okay, we'll use that as a starting point, but the problem is again, we're not looking for a root, we're looking for where this is maximum. So why am I using bisect here or thinking about bisect? Okay, and that's because in Calc 1, when you spent a while talking about maximums and minimums and optimization problems, really the first step oftentimes, once you had the equations you needed to work with, it was to take the first derivative, okay, right? Because that peak that we were looking at, that's going to happen when the first derivative is 0. Okay, so why don't we actually also go ahead and take our derivative, and that's what we'll use the bisect function on. I'll call it di. Okay. There we go. And so this will also be a function of t, and I'm going to just copy and paste this twice because we're going to have to use the product rule, and it's not going to look significantly different one term from the other. So if we were to take the derivative of this first function here, 9e to the minus t. All that would change is you'd have a negative here, and we'd still have our second function, and then plus our first function, and then times the derivative of our second function. So I just need to change this to a cosine and multiply by 2 times pi. And so there's our derivative. Okay. And so let's see if this works out. Let's go ahead and hit run here. Okay. And so you can see our root. Okay. And let's say we want to test this out maybe a little bit better. Let's maybe say we'll take that answer and we'll go ahead and we'll plug it into I here. So maybe I'll say, how about we call this x max? That sounds good. And let's try to get our y max here as well. And our y max is going to be I of x max. Okay. All right. Let's go ahead and hit run. All right, and let's see what we have here. Looks like we have our x max and our y max. Well, let's maybe put maybe a horizontal line at the y max and see if that matches our work here. So to get our horizontal line, we could do this a few ways. We could say, that we have y equals at t of, and our function's just not going to be very interesting. It could be the 7.0982. Okay. And what we could do is after our plot here, okay, and actually this also means that we could comment the rest of this stuff out here now. We'll hit hold on, plot, and we can do t, comma, y. Let's go ahead and hit run, see if we get any error messages. We got an error message here because the plot command is expecting not a function here, but a vector. Okay, so I could make this just I without the at t. And to fix y here, we can actually do this in kind of a creative way. So what we need for y is we really just need a vector that contains 7.0982 over and over again. It just needs to be the same length as t. Okay, so one thing you could do is you could say, hey, I'm not sure what the length of t is, although it's 1 by 100. I can see this over here in my workspace. And then another thing we could do is then we could create a vector of ones. And there's, just like we have that zeros command, we have a ones command. Okay. And so I would like this vector of ones to be 1 by whatever the length of the vector t is. Okay. And now is what I'm going to do to create this vector y that I want is I'm just going to take my ones and I'm going to multiply it by the 7.0982. Okay. And now let's go ahead and plot and see what we have here. Okay. I think everything else looks good. Alright, there it is. And so what this shows is that our derivative and bisect function did lead us to the correct answer. It did lead us to the maximum that we were looking for. You could also verify that this is at least a local maximum, right, by taking the second derivative and seeing whether it's positive or negative. But since we have this visual representation, I think we can be satisfied with what we have here.